Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. Today we are going to discuss about the module Martenistic Transformation and Crystallography from the paper Functional Materials. So students, let us see what we are going to learn in this module. First, detailed study of Martenistic transformations. Second, orientation relationships. Third, crystallography and phenomenological theory of Martensite phase. So students, let us start with a basic introduction about this module. Over the past decade, non-linear thermoelasticity has been developed for Martenistic transformations, especially for the study of reversible Martenistic transformations in shape memory materials. The theory has produced specific quantitative predictions, some of which are being used as the basis of alloy development programs and others which await experimental verifications. Some of these predictions are rather unexpected and have led to revisions of the fundamentals of Martenistic transformations. Crystallographic phenomenological theory of Martenistic transformation is based on the assumption that there should be no average distortion at the matrix Martensite interface, that is, at the habit plane, and furthermore, this interface should remain unrotated during the transformation. Only by using this basic condition and lattice parameters of austenite and martensite phases, and by assuming lattice invariant strain system, the theory can predict the habit plane indices. Orientation relationships between the austenite and martensite lattices, and also the magnitude of the lattice invariant shear associated with the Martenistic transformation. Martensitic transformation. Some of the important characteristics of this transformation are: first, it is an inelastic deformation of the crystal lattice. Second, it is a diffusion-less transformation. Third, it is independent of time and depends only on the temperature of transformation, and also on the strain in the crystal lattice. Fourth, it is the parent and product phases coexist during transformation. Fifth, there is a one-to-one correspondence between the atoms in the parent and the product phase. Sixth, there is one-to-one correspondence also in the directions and the planes between the parent and the product phase. Seventh characteristic is that the transformation reduces volumetric and shear strain along well-defined planes. Lastly, since the crystal structure of Martensite phase has lower symmetry, several variants of Martensite can be formed from the same parent phase crystal. FCC to BCT transformation. Now, students, let us look at the transformation at the lattice level. In order to keep things simple and without losing the generality, we can take the case of FCC to BCT transformation, which is very common in nickel titanium alloys. If we put two FCC unit cells together, it can be seen to include a BCT unit cell within it, which is also shown in the figure, which is showing the Bain's model for diffusion-less transformation from FCC to BCT. Now suppose that the C-axis of this new BCT cell is contracted and the A and the B axis of the cell are expanded so as to match the size of the BCT cell of the product phase Martensite. In effect, this simple deformation manipulation can result in the transformation from one kind of structure to the another. This transformation was originally proposed by Bain, and the strain required to make this transformation is called as the Bain strain. Deformation matrix can also be easily obtained for making this transformation. FCC to BCT transformation. Equivalent strain and lattice deformation matrix can be calculated. This mechanism will be different for different alloys. However, it is always possible to create the product phase from the parent phase by the combination of elongation, contraction, and shear along certain directions. Habit plane. During the transformation, when the temperature is lowered to Ms, Martensite phase starts to form in the parent phase matrix. The transformation does not go to the completion unless the temperature remains above MF. So, for the temperature between Ms and MF, both the parent phase and the Martensite phase coexist. Since the product phase is formed by lattice deformation, or we can say the transformation of the original lattice, there has to be a relation between the parent and the product phase. Moreover, there will also be certain planes and directions which are similar in both the phases. Now, the Martensite phase will always like to grow along the planes which are common to both the phases. Such planes are called as habit planes. So this figure shows the growth of Martensitic phase under constraint, that is the bottom one, and the unconstrained transformation is shown by the top one. Martensitic transformation also occurs with certain skewness in the structure, and therefore the product phase can be grown under two conditions: constrained and unconstrained. So these two configurations have been already explained in the figure. However, here the planes at which the martensite grows remains the same. One may notice some curvature in the second case of constrained transformation. However, the curvature shown in the picture is exaggerated, and the actual plane is still very similar to the one shown in the unconstrained configuration. Orientation relationships. Since there is a 1-to-1 relation between the atoms of parent or to the product phase, there also has to be the orientation relationship between the two lattice. So usually the close packed planes are parallel or nearly parallel, and usually the corresponding directions within these planes are roughly parallel. So, using the Bain model, we can obtain a correspondence in the directions and the planes between the parent and the Martensite phase, and we saw that the 001 gamma plane is parallel to 001 alpha, and 1 bar 0 gamma is parallel to 100 alpha. Third, 110 gamma is parallel to 010 alpha. So, but how do the XYZ P and HKL-P corresponds to XYZ-M and HKL-M, where P and M corresponds to parent and Martensite phase. So under Bain's model, even though there is a deformation of the product's lattice, the deformation does not change the Miller indices, and hence the coordinates obtained using coordinate transformation, or they can give the 1-to-1 relation of the planes and the directions. So the experimentally observed orientation relationships, they are irrational, and these are described by Kurjumov-Sachs orientations. This figure shows the stereographic representation of Kurjumov-Sachs and Nishiyama-Wassermann orientation relationships. These stereograms, they are both centered on 1 gamma parallel to 011 alpha. It is seen that the NW orientation or the Nishiyama-Wassermann orientation can be generated from Kurjumov-Sachs by an appropriate small rotation of 5.5 degree about 011 alpha. Only a few of the poles are marked to allow a comparison with the Bain orientation relationship. The neighboring pairs of poles would superimpose exactly for the Bain orientation. Lattice deformation. So students, this matrix, that is B bar, shows the lattice deformation matrix with respect to the new coordinate axis, where lattice parameter of FCC is A0 and that of BCT are A and C. So now B is equal to R multiplied by B bar multiplied by R transpose, where B corresponds to the lattice deformation matrix with respect to the parent phase, where R is the rotation matrix. Lattice correspondence. So lattice correspondence, basically the correspondence in the directions and the planes between the parent and the Martensite. So here half 0 P and half 0 P, where in the previous case there was a half bar, corresponds to 100 M and 010 M respectively. So how do the XYZP and HKLP corresponds to XYZM and HKLM? They are nothing but they corresponds to XYZM and HKLM by coordinate transformation. Coordinate transformation. So students, as you can see from these matrices, how X, Y, Z, they are transformed into capital H, K, L. The transformation from FCC to BCT, that is, the transformation from new to old, occur by lattice deformation. However, the Miller indices are invariant under this transformation. Thus, the matrix that is used for lattice transformation can also be used for finding the plane and direction correspondence. Correspondence variants. The Bain transformation model that we used earlier assumed the C-axis to be aligned along the Z-axis, and hence the contraction was done along the Z-axis as shown in this figure. However, the C-axis can be along any other direction as well, X or Y, and hence contraction may have to be done along those axes. Hence, the transformation can be described by three different matrices, and hence three correspondence variants are possible for FCC to BCT transformations. Orientation relations revisited. So students, we are recalling the orientation relations. The Martenistic transformation can be given by a matrix which constitutes of three components. First is lattice deformation matrix. Second is a lattice invariant shear matrix, and third is lattice rotation matrix. Combined effect of Bain strain that is lattice deformation, and rigid body rotation gives invariant line strain, which is clear from the picture where parent phase is represented by a sphere and the product phase is represented by a deformed sphere or ellipsoid. Orientation relations revisited. Now students, this figure, that is the part A of the figure, shows the FCC parent phase, which is represented as the sphere where Wx and Yz are the diameters. The B part of the figure shows the Bain strain results in the ellipsoid and each and every plane is distorted. C figure shows that the invariant line strain is obtained by providing rigid body rotation through an angle theta. Orientation relations, combined effect of Bain strain and rigid body rotation gives invariant line strain ILS. However, this would lead to shape change which is not observed. This can be resolved if the shape changing transformation given by PZ is cancelled macroscopically by an inhomogeneous lattice invariant deformation. Students, this figure shows the various components of Martensitic transformation. Now, as noted from figure A, B and C, which shows a simple transformation from the parent phase, that is austenite, then to the observed shape or the wrong structure, and then to the Martensite phase or the product phase with a change in the shape. Now, the figures from C to D, that is the part C to D, shows the lattice invariant shear accommodated by twin. Then the figure from C to E, the transformation from C to E, shows the lattice invariant shear accommodated by slip. The process does not cause any change to the structure of martensite. In shape memory alloys, twinning is the most commonly observed and is the cause of SME or the shape memory effect. Phenomenological theory of Martensite crystallography. The aforementioned theory explains all the observed features of Martensite crystallography. The orientation relationship is predicted by deducing the rotation needed to change the Bain strain into an ILS. the habit planes do not have rational indices because the amount of lattice invariant deformation needed to recover the correct macroscopic shape is not usually rational. It also predicts the substructure in the plates of Martensite, that is either the twins or the slip steps. So students, let us summarize what we have learned in this module. First, Martenistic transformations have been discussed in detail, taking the example of FCC to BCT transformation in nickel titanium alloy. Second, Kurzarbov, Sachs and Nishiyama-Wasserman orientations relationships were explained. Third, the Bain model used to obtain a correspondence in the directions and the planes between the parent and the Martensite phase were discussed. The phenomenological theory of Martensite crystallography was also explained, and also the three constituents, that is lattice deformation, lattice invariant shear and lattice rotation were explained. Thank you.